Okay, so in the Chapter 11 fly-through, I lied. There are 4 things that we're going to talk about. And one of them we already talked a little bit about yesterday. We're going to sort of review it. There are a bunch of notes for Chapter 12, but these are kind of the 4 big ideas. And that first one is the thing that we talked about in your lab. Any gas, methane, ethane, propane, butane, oxygen, nitrogen, hydrogen, water vapor, carbon dioxide, carbon monoxide, any gas at STP has a volume of what? 22.4 liters. That's the whole idea behind molar gas, standard molar volume. Okay, so that's the whole idea there. Any gas at STP, 1 mole of it has a volume of 22.4 liters. That's pretty easy. The second, we actually sort of skipped one step, which is I didn't talk about volume ratios. So you've done stoichiometry and you're good at it. If I tell you that, in the equation we had, in the reaction we had yesterday, if I tell you that, if I give you this reaction, which is what we did, and we have to balance this, of course, and there it is, and I tell you have 1 mole of magnesium, you can immediately tell me how many moles of hydrogen gas you produce. Easy breezy. How do you do it? Stoichiometry. You use the coefficients. You know that, oh, well, I start with 1 mole of magnesium, and for every 1 mole of magnesium that I use, I'm going to generate 1 mole of H2, and so I get 1 mole of H2. And if I told you had 11.3 moles of magnesium, you could figure that out. And if I told you that you had 642 moles of magnesium, you could figure that out. You get the picture. You're clever critters. Well, using those coefficients is fantastic. And here's the even cooler part. If you have a reaction in which all of the reactants and all of the products are gases, does this ever happen? Yes. Name me one. We started to talk about this yesterday when I talked about firefighting, or 2 days ago. Propane and what? Oxygen. Combust. Yeah, you have combustion of propane, so let's write that. Here it is. Combustion of propane. Great. CH3, oops. C3H8 plus 5O2 yields 3CO2 plus 4H2O. Who here has ever seen propane combust? Propane torches, propane grills, propane lanterns. You've probably all seen propane combust. Is this happening at like a temperature where water would be a liquid? No. Every single thing here is a gas. So, all gases. You've got gaseous propane combusting with gaseous oxygen from the atmosphere, producing gaseous CO2 and gaseous water. Here's the awesome part. If every single thing in this reaction is under the same conditions of temperature and pressure, and would they be? Yeah. They're together. They're reacting together. They're obviously in the same place. They're under the same conditions of temp and pressure. As long as they're all under the same conditions, you can use the coefficients as volume ratios. Same way you used mole ratios in general stoichiometry, you use those as volume ratios. So given a problem like, if 152.0 milliliters of propane combust, what volume of CO2 is produced? Wait, volume changes with pressure and temperature, right? Yeah, it does. But everything here is a gas, and therefore you can use those coefficients as a volume ratio. So when we set up our factor label, it's so stinking easy. We always start with what? Given. So we start with our given, and now we know that we have to have a volume of CH3 to cancel. We want to end up in a volume of CO2. Well, for every 1 milliliter of CH3 that combusts, you're going to produce 3 milliliters of CO2. For every liter of CO2, every liter of propane that combusts, you're going to produce 3 liters of CO2. So it's just volume for volume. So since I'm in milliliters, I can use milliliters. It does not matter what units of volume you use. You could use, square cubic feet, though you would get laughed at because this is science. We don't do feet. For every 1 milliliter of propane that combusts, we generate 3 milliliters of CO2. And actually, I can get rid of that because we're done. That's it. It's one step. These are nice, aren't they? I like them. So 152 times 3. The combustion of 152 milliliters of C3H8 is going to produce 456.0 milliliters of CO2. About a half a liter of CO2. Aren't those nice? Now, what are the conditions on using something like this? Everything has to be a gas. You have to go from a gas to a gas. Everything has to be under the same conditions of temperature and pressure. Well, if they're reacting together, they are under the same conditions of temperature and pressure. So if things are in a reaction together, that's where, this is applicable. Okay, so standard molar volumes, volume ratios, good. Ideal gas law is a way to think about what volume a given quantity of a gas will take up. So if we go from the example, if we just go ahead and we can keep using this equation because, hey, we've already balanced it. So let's copy that. If we get something that says, well, we run the combustion of propane and we produce 5 moles of water vapor. So let me write the question. Okay, so we're doing the combustion of propane again. Well, let's say you're not told what volume of anything reacts. You're just told, hey, guess what? You made 5 moles of water vapor. Under these conditions, what's the volume of that water vapor? So how much space is that water vapor going to take up? Well, we've got pressure, we've got temperature, we've got number of moles, we're looking for volume. This is where, boom, 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 the ideal gas law comes in. So we started to talk about this briefly yesterday, and the ideal gas law is this. PV equals nRT. And the places that this applies are when you've got pressure, volume, number of moles, and temperature being related to one another. Anytime that those are the 4 sort of actors in play, you want to look to your ideal gas law. So let's sort of match these up. Is pressure specified? Yes. Right there. Is temperature specified? Yes. Right there. Are number of moles specified? Yes. Right there. What are we looking for? Volume. We're looking for volume. And remember, we briefly talked about this yesterday. R is the ideal gas constant. R is the ideal gas constant. And it's a lookup, 62.4 torr, let's see, torr liters over mole kelvins, or 0.0821 ATM liters over mole kelvins. You can look them up. You can also calculate them. Doesn't matter. Just the thing you have to make sure of is that you're using the right R for the units your pressure is in. So let's actually do the ideal gas law on this problem. Okay, so 2 things to do when you're doing any kind of ideal gas law problem, just like you did in the combined gas law problems. List your variables. It helps you. And even though R isn't a variable, I usually list R because it forces me to look at my units for pressure and say, oh, which ideal gas constant do I want to use? And I think it's, I don't know what page it is in your book. But anyway, we're going to use the one that's in torr, which is 62.4 torr liters over mole kelvins. And to double check my numbers for that, because I didn't look it up, I'm going to multiply 760 times 22.4 liters divided by 1 mole times 273. So 760 times 22.4 is that, divided by 273. Yep, 62.4. Okay, I was right. I always like to double check myself though, because I screw it up. Okay, so the next thing I want to do is rearrange for the variable I'm solving for, and this is an easy rearrangement because all I have to do to isolate V is divide both sides by P. Couldn't be much easier. So V equals nRT over P. That's it. It's algebra. Have you seen this equation in math? Did I ask you this yesterday? You've never done this. Okay. So go ahead and plug in your numbers and we'll find a volume. So we have all our numbers written in. If you write your units in with these, here's what that does for you. It allows you to double check your rearrangement by canceling. So I can look at this and go, okay, well, moles cancel, kelvins cancel, torrs cancel, I'm left with liters. Is that the unit that I want? Am I looking for volume? Yeah. So it's a nice helpful thing. Let's get our raw answer. Okay, so you get a raw answer of 293.883871. Final answer, we have 3 sig figs. I did go back and give myself some more sig figs by rewriting that. It's 5.00. So we have 3 sig figs, 294. Fairly easy, fairly straightforward. Let me give you some practice problems for that, and I'll give you some time to work and put the radio on, and then we'll come back and do the one last thing. Okay, these get you some practice with molar volumes and ideal gas law. So numbers 11 through 14, part A only, so 11, 12, 13, 14, that's 4 problems. 16, 17, 18, that's another 6. You've got 10 problems, parts A and C only, don't do them all. And basically we're going to sit here and work and listen to the radio. Hey, you know what? Scratch that. Make that part B, not part A, because the part A ones are the, like, really stupid ones. Are you guys listening? No, just skip 11 altogether. So 12 through 14, part B only. Don't do the A's. Sorry about that.
Did you want us to do the A's on 16?
Yeah, those I do want you to do. This part of the assignment does stand as written. Some of the good questions that were brought up. If you're using the ideal gas law, does it matter which R you choose? Do the units matter? Well, of course they do. But if you're finding pressure, do they matter? No, but what you have to know is that whatever R you pick, so if you pick 62.4 torr liters over mole Kelvin, your answer for pressure is going to be in torr. If you pick the one that's ATM liters over mole Kelvin, your answer for pressure is going to be in ATMs. So the other question that was then asked is, what if you're given a volume, but your volume is in milliliters? Does that matter? It does, because that won't cancel liters. Whoops. That will not cancel liters. They don't match. Your units have to match. So if you're given volume in milliliters, you do have to convert to liters. So here we have, this is the reaction you ran in the lab. You've got hydrochloric acid and magnesium. You form magnesium chloride and hydrogen gas. Only one of the reactants or products here is a gas. Everything else is a solid or a liquid, or an aqueous solution. You've got an aqueous solution here. You've got a solid here. This is also an aqueous solution. I guess you don't have any liquids. Can you use what you just found to, can you use the ideal gas law on this? You sure can't put something like magnesium into the ideal gas law. It's not a gas. You can't put hydrochloric acid into the ideal gas law. It's not a gas. So what if you are asked something like 200 grams of magnesium react. The reaction is run at 25 Celsius and 767 torr. That would be, we took a pressure reading in the lab that day. What volume of hydrogen is produced? Well, if this was happening at STP, we could figure out how many moles of hydrogen are produced and just say, oh, that many times 22.4. But we're not at STP here. So these are the kind of problems, and these are actually more common. So I'm happy for you that we're not doing these and you're being tested on them, but I'm sad because I think these are really the more common kinds of problems, because you have a lot of reactions that occur where some things are solids, some things are gases. And, how do you handle that? It's a two-step process. So here we have a given that is a not gas. And if you have a given that's not gaseous, you have to start off with plain old stinking Chapter 9 stoichiometry to figure out, so we have two tools we can use. We have a factor label like we did in Chapter 9 that allows us to go from moles or grams of one substance to moles or grams of another. And we have the ideal gas law that allows us to go from pressure, volume, temperature conditions to number of moles, or number of moles to volume, pressure, or temperature conditions. So whichever one of those two tools you start off with, it depends on your given. So here, we're given something that's a solid, and we're going to start off with a factor label that starts with our given. So 200.0 grams magnesium. Is it 24.31? Do I have the molar mass of magnesium correct? So we go through this factor label process, and what are we going to try to get out of this? Well, we want moles of H2, because that is then something that we can put into PV equals nRT, because the final thing we're asking for is that. And we need to have a number of moles that we can put into an ideal gas law problem. So how many mole? 1 mole of magnesium, the stoichiometry is really nice on this, to 1 mole of H2. We get a raw number, and we get 8.227, and it goes on and on and on. That then is a number of moles of H2 that we can put into an ideal gas law problem to find the volume. So there are basically two kinds of problems here. Either you start with a factor label or you start with an ideal gas law calculation. Like I said, you're not going to be testing on these, so I'm not going to spend a lot of time. But I wanted you to be aware of these. If you're given something that's a gas, either number of moles or a volume of a gas, then you have to go with the ideal gas law first and then do the stoichiometry factor label. That was pretty painless, I think, right? Shall we finish this? Let's finish it. We can. Okay, so we're taking the ideal gas law. We have our pressure and our temperature conditions. We now have number of moles. Pressure was 767.0 torr. Temperature was 25, which is 298 Kelvin. Number of moles, 8.227, on and on and on, moles. And we want to, I gave the pressure in torr, so we would use the ideal gas constant in torr, 62.4 torr liters over mole kelvins. Rearrange to solve for V. V equals nRT over P. V equals. We've got our plugins there, and we cancel out units, make sure that we've got our rearrangement correct. We end up in liters, which is just what we want. So we get a raw number for volume of 199.457, on and on. I think we had, how many sig figs? 2. So we would call it 2.0 times 10 to the second liters. Now here's the funny thing that I just realized. I'm a dork. So remember I said I was doing calculations to see if we could manage this with the dilute hydrochloric acid. And the concern is you want to have enough acid volume to react all the magnesium, but you don't want to generate so much gas that you empty the beerette. Well, duh. If I had been thinking, I would have done this calculation instead of what I did. What I did was far stupider. Trust me. So if I say, well, I want them to generate 35 milliliters of gas, which most of you generated, what, between 10 and 15, I think? Because we used a really small chunk of magnesium. So if I said, okay, we've got this reaction. I want them to end up generating about 30 milliliters of gas. What mass of magnesium do we need? That's how you would figure this out. So you start off then, let's do it. Okay, so if I want 0.035 liters of hydrogen gas, what mass of magnesium do I want? And we're assuming that this is going to be at about 25 Celsius and 700 and, what was it the other day, 765? Oops. Now, of course, this leaves out, in terms of gas volume, the fact that you have that partial pressure of water. So this would get you a rough number. Wouldn't be perfect, and there'd be a way to make it perfect, but we're not going to do that. So here, I have a volume of hydrogen. I want a mass of magnesium. I have to start with the ideal gas law. So I'll start with PV equals nRT, and what I want to know is how many moles of hydrogen am I going to get if I get 0.035 liters of hydrogen under those conditions. So I would plug in all my numbers, solve first for that, so PV over RT equals N, and bell's going to ring in a second. I think you kind of see where this is going. Like I said, it's not going to be on your quiz. I'm not giving you a homework problem on it, but I just want you to realize these are the more common applications of this kind of thing. So if you're going on in chemistry, you know, you may or may not see this. That's it. That was a fly-through, drive-by, quick attack on Chapter 11.